Hey, welcome. So today's topic is, you can read it, numerical integration. It's basically what we're going to try to do is estimate an integral when we don't have a defined function. We might just have a table of values, or usually we'll have a table of values to work with. And it builds on the concept of what are called Riemann sums. And we've sort of worked with Riemann sums earlier on. We didn't necessarily call them that, and I might have my I before E, and I'm not sure. This way it looks better. I don't know which way it looks better. It's one of these two. I think it's the second one. In terms of spelling, it's a man's name. I should know how to spell it. But the basic idea is that it goes back to the finding integrals using rectangles. Okay, and so we've got several options that we can use. We can use the left endpoints. And so when we use the left endpoints, that just means that our rectangles start on the left. So if I were to draw any rectangle there, and then there, pretend these are rectangles. I'm doing the best I really can. And then there. And then I'm just going to carry it all the way through. And then there. And then it's a little dicey because I think we go outside the edge a little bit. And then finally, there-ish. Okay, so we could find the area of all those rectangles if we knew something about the function, or we could count squares or something like that. We could estimate. It'd be off by a little, right? Because we're a little under in this area, we're a little under in this area, that area. Here we're about even, and here we're a little over. So we wouldn't get an accurate answer, but we'd get an approximation. And sometimes that's the best we can do. So we would just use height times width, get the areas, boom, add them up, get an approximation to the integral. Because remember, the integral is just the area under the curve. That's one sort of working definition that we might have. If we use the right endpoints, well, we make our rectangles start on the right, okay? And so we get a bunch of rectangles that look like this. Okay. And there it is. And this one's going to be a little bit under. And, oops, sorry. And this one, pretend they're rectangles, sorry. Okay, so in this case, we use the right endpoints, and so we'd get a little bit of an overestimate because we'd have all this outside. This one's a little outside, this one's a little under, that one's a little under, but I think my over, so more than my under. So using the right endpoints, we'd get a little bit of an overestimate. All right. We could use the midpoints. And so with the midpoints, what we do is we pick the middle of the little segment that we're talking about, and we draw our rectangles there, okay? Like so. And then we draw a rectangle there, like so. And then we draw the rectangle there. Okay, get the idea? Okay, and so in this case, we're sort of splitting the difference, and we might get, a better estimate in this particular case because we're not off by a whole lot, where we're over on one side, we're under on the other. Okay, and you might figure out that the answer to this one is sort of the average of the left and the right endpoints because it's in the middle. Okay, so sometimes we'll use a midpoint to test this out. We'll get to what this all means eventually, but right now let's talk about the trapezoids. So with the trapezoids, what we do is we make some trapezoids. So we basically do a straight line thing that goes from endpoint to endpoint. And you can see, if we had my intervals a little shorter, my trapezoids would be pretty good representation of the curve. We're just kind of doing dot to dot, point to point. They're awful, but you get the idea. Okay. So let's see if I have a slide to go. Okay, so I need to get a little more detail on this trapezoids. So if I want to get the trapezoids, if you look at it, these trapezoids are just sideways sort of trapezoids. So this side and that side are parallel to each other, and this is my height right there. Okay, we're going to call my height delta x. We'll call this one, well, this one's really the f of a, right? This is the f of x sub 1, right? The height of the thing. This would be the f of x sub 2, x sub 3, x sub 4, and then finally we'd end up with the f of b, okay? So if I look at my first trapezoid, trapezoid number 1, its area is base 1, which we're going to call the f of a, plus the f of x sub 1. Okay, so add the two. Remember how to find the area of a trapezoid is b1 plus b2 divided by 2 times the height. Okay, so b1 plus b2 divided by 2, the height is delta x. If I want to find the area of trapezoid number 2, which is this one, area of trapezoid number 2, I haven't done these in a while, so we would have the f of x sub 1 plus the f of x sub 2 divided by 2 multiplied by delta x. If I wanted to find the third trapezoid, okay, I'd have the f of x sub 2 plus the f of x sub 3 probably divided by 2 times delta x. And I can do that with every trapezoid. And if I wanted to do whatever this last trapezoid is, the area of the last one, I'd have the f of, I'm just going to say, xn minus 1, okay, the last one, plus the f of b over 2 times delta x. So to find the area of the whole thing, I'd have to add all these pieces up. Okay, and so we could do this easily like this. We could do it in little pieces. So draw that last line in. But what we might notice is a pattern. If I enter all these in, my total area, I'm going to have, all of them have that delta x over 2. So we may as well pull that out in the front. Okay, we're going to multiply that by the f of a, which is my first endpoint. Notice the f of x sub 1 shows up in both of these equations. That shows up here, and it shows up there. The f of x sub 2 shows up here, shows up there. The f of x sub 3 would show up here and there. The n plus 1 would show up here and there. The f of b only shows up one time at the end. So anything that's in the middle, we would count twice. Okay, plus dot, 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 dot. Finally, we'd get to the f of b, my other endpoint. And so with a trapezoid, you can work your way through separately each piece, and sometimes if these aren't even widths, then you need to just figure out the areas of all the little trapezoids and add them all together. If they're even widths, you can kind of do a delta x over 2 and double any of the heights in the middle. Okay, that's the trapezoid. It's a trapezoid rule sort of thing. I want to try to have that, I don't know, memorized, but somehow at least familiar with it. So the question is, which is more accurate? Which one is more accurate, left, right, midpoint, or trapezoid? And the answer is, it depends. What's it depend on? Depends largely on the shape of the curve. Okay, if I have a curve that looks like this sort of thing, where it's concave up, if I do my left endpoints, I get an underage, right? If I do my right endpoints, I get an overage. If I do my midpoints, I get probably a little closer to accurate. And if I do a trapezoid, I might be probably the closest in this case. Okay? Sometimes a question will ask you to rank these, which one's going to give you the greatest area, which one's going to give you the smallest amount of area. And so then you have to kind of look at, well, what's the concavity of the shape, draw in the little rectangles, and make an educated guess. If I were to go with this one, I would say my left endpoints give me the smallest, and then probably my right endpoints are going to give me the largest, and then it's probably a guessing game between the midpoints and the trapezoids. Trapezoids are probably going to be a little under because the way this concavity, no, let's say, will it be over? Drawing this, bigger. So if I look at the bigger one, I'm going to be over on the trapezoid. So I'm going to go midpoint and then trapezoid. So left, midpoint, trapezoid. I just kind of looked with the concavity. If I were to just draw the big giant trapezoid, it'd have extra area there. Okay, not probably as much as I'd get with the jagged right-handed sums. Okay, so you just, that might be a question that you come across. Let's work some problems. Okay, so water flows into a boat through a leak at a rate given by the differentiable equation L of t. And we don't know what that equation is. We don't need to know. The table shows the flow rate measurements that were taken every 2 minutes for the first 20 minutes. Okay. And what they want us to do is use a midpoint, it must be RIE, Riemann sum, with 4 equal subintervals to approximate the integral of this. Okay, so we're going to do 4 equal subintervals, and we've got from 0 to 20. So there's subinterval number 1, number 2, number 3. Oh, so did I do that right? 0 to 4. Oh, sorry, 0 to 4, 4 to 8, 8 to 12, Did I say 4? Oh, my goodness. Wait. What's this? Okay. So we're going to break this into 4 equal pieces. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 0 to 4 is 1. 4 to 8 is another. 8 to 12. 12 to 16. 16 to 20. Did I do that right? That's 5 equal subintervals. I think I'm going to go with 5 equal subintervals. Can I do that? No. Try that again. 0 to 4. Wait, overthought this, or did I underthink it? I really think I want this to be 5 equal subintervals. I'm thinking on the fly here. 48, 12, 12 to 16, 16 to 20. I think that's what I want. I want 5 equal subintervals. So let's just adjust that so it says 5 equal subintervals. And so if we're using a midpoint Riemann sum, what we use for our height is the middle of the interval. So in the interval from 0 to 4, that's the height that I'm going to use. In the interval from 4 to 8, that's the height that I'm going to use. In the interval from 8 to 12, I'm going to use this one. And from 12 to 16, I'm going to use that height. And from 16 to 20, I'm going to use that height. Okay? So I'm just going to make some rectangles. All of my rectangles are 4 wide, right? So I'm going to end up with 4 times 0.7 plus 4 times 1.3 plus 4 times 1.2 plus 4 times 1.4 plus 4 times 1.0. Okay? And so if I, and I could have just done 4 times the sum of 0.7, 1.2, 1.4, 1.0. Okay, and so if I do this actual math out, which I'm not going to at this particular moment, I would get the integral. Okay, I'd get an approximation of the integral without having a function. And the question is, what's the solution to that definite integral tell you? So when we get this answer, what does it actually tell us? Hopefully, what you're thinking is, hey, we integrated a rate, so what do we get? We get a total. So the integral of a rate is a total. Okay? What are we doing for time? It seems like I'm running long. Oh yeah, I'm running a little long, but that's okay. So some other questions that we could answer with this particular thing is, was the rate of change equal to 0 at some point during the first 20 minutes? Go back and look. What's the average rate of change during the first 8 minutes? We could answer those sort of questions. When we have a table, of values, we can say, well, those 2 questions. I don't know what I'm saying. We're just talking now. All right, so the temperature at the top of Mount Mansfield is represented by a differentiable function, m of t. Temperature data for the first 15 days of the month is recorded every 3 days and listed in the table below. So we want to use the data in the table and a trapezoidal sum to find the average temperature during the 15-day period. Okay, so remember, if we're finding the average temperature, we're going to do the integral. I made the symbol, divided by the interval, right? Okay, so the integral part, we're going to use our trapezoid rule. And with the trapezoid rule, if you remember, we're going to do delta x. In this case, they're all groups of 3, divided by 2. And then we're going to just total up use our temperature data as we go. Okay, and remember that this one counts once, this one counts twice, 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 and then just once, because these ones show up in 2 of our trapezoids, so we have to get that in there. So we would just be a matter of 23 plus twice 32 plus twice 24 plus twice 19, well, I did that, plus twice 8 plus 12. Okay, and we get that total. That would be the integral part. And then in this case, what we would do is we take that answer and divide it by 15. Okay, so this is sort of the temperature, and we would find the area. That would give us kind of like the total temperature day thing. And then if we divide it by the number of days, that would give us my average temperature. Okay, so with the trapezoid rule and the table of data, we just use the bunch of trapezoids, boom, 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 double up the ones in the middle, and answer. You can check that answer and see if it reasonably makes sense. It should turn out to be a reasonable temperature, probably someplace in the, what would I say, probably the low 20s maybe, someplace around there, given that temperature data. So check that, do the actual math on it, and go. Other questions? Oh, I don't know, somewhere I thought I had other questions that we could answer, but same sort of questions that we had with that one we could answer with this, though. You know, was there a place where the rate of change was equal to 0? Was there, what was the, I don't know, total temperature or something like that? All right, so we'll go to there, go to that one. So again, that's actually from Expedition Everest at Disney. You're in a little thing, you get up to here and you go backwards back into the cave. The Yeti gets you. But it'd be an interesting, you know, curve. We wouldn't have a function for it, but we could figure out the area if we had enough data points just by putting some rectangles or trapezoids or something like that in there and approximating the shape. Okay, so numerical integration. I think I'm running long here. I'm pretty sure 16 minutes. Oh my gosh. But let's go back to this for you for a second. Back to there. Thanks for watching. Hope you learned something. We'll work on this for a couple days in class. Make sure that it gets, because these are pretty good problems to show up on an AP test. We'll see you soon. Have a beautiful day.